This video deals with measurement, how to determine a way to fairly measure and compare characteristics that can't be measured with a scale or a ruler. The objectives of this chapter are to define measurement, understand its use and the importance of using it in staffing decisions, understand reliability, review the different ways it can be measured, define validity and consider the relationship between reliability and validity, compare and contrast the two types of validation studies typically conducted. Consider how validity generalization affects and informs the validation of measures in staffing, and to review the primary ways assessment data can be collected. We start with why measurement is important and how we might use measures. Measures are the substitutes for the scale or ruler we might use to assess a physical object. The job analysis identifies KSAOs needed for a specific job, but how do we fairly evaluate the extent to which a candidate possesses one or more KSAOs? And then how do we compare one candidate to another? Measures give us a way to do that. The measurement process is pretty straightforward. First, we choose the KSAO or attribute we'd like to measure. Let's use customer service as an example. Second, we determine a clear definition of the attribute. Let's say customer service is the process of ensuring customer satisfaction with a product or service. Third, we construct a measure of the attribute. For example, we could use customer survey responses after talking with a customer service rep. Fourth, we use a measure to numerically gauge the attribute. For example, Service Rep A has an average 3.7 rating, which Service Rep B has an average 4.2 rating. As a result of this process, the scores become our measure of the attribute and actually become a substitute for the definition. Now we'll look at some key concepts of measurement. To review the terminology, measurement is substituting numbers for levels of an attribute. Scores are the numbers, and correlation is the relationship between two sets of scores. This chart shows how we might develop a measurement for an IT analyst. First, we examine the job analysis to see that knowledge of programming languages is an important KSAO, and probably in the job specification. Then we figure out how to measure that knowledge. In this case, we'll use a test. We'll give the test to job applicants, score the tests, and evaluate the applicant's performance relative to each other and to the requirements of the job. For example, we would probably have a minimum score needed to, quote, pass the test. Once we compare the applicant's scores, we select the best candidate. Obviously, if we're replacing an attribute with a number, we want the number to be accurate. It's important that the test be fair and that it measures what we want it to measure. That means we make sure there's no contamination by items not part of the attribute, and that the scores actually represent different levels of the attribute being measured. Standardized measures are the way we accomplish this goal. We make sure that we measure the same content, in other words, everyone takes the exact same test. We administer the test the same way for everyone, in other words, everyone has the same time limit and materials available to them. And we use the same process for assigning numbers to all test results. In other words, a scoring key is developed in advance and used on all tests. In addition to standardization are the different levels or scales of measurement. The four common levels of measurement are nominal, ordinal, interval, or ratio. For nominal, numbers are randomly assigned to the categories, but those category numbers are just labels and have no ranking. It's like randomly choosing different color file folders to organize your papers. Ordinal. This indicates ordering something from best to worst, or high to low. For example, you could order your candidates from best to worst, but ordinal doesn't tell you how closely those candidates are to each other. For example, if they had grades instead of numbers, one group might all fall from the A plus to A minus range, and the next group might fall from A to C minus. Interval. This is also rank order, but the distance between 1 and 2 is the same as the distance between 3 and 4. Note, this is difficult to achieve in staffing, so often ordinal and interval are combined. Ratio. This is still a measure, but also has equal differences between scale points and has absolute zero. For example, if you counted the number of tests you took this semester and the answer was 20, then you compare that to your roommate who took 10. The frequency of tests by your roommate was half of yours. Also, if you took 0 tests, then your frequency would be 0. Another division in measurement is whether the measures are objective or subjective. Simply put, objective implies that there's an impartial method, such as an objective test, used to measure something. An example would be the number of free throws completed in a basketball game. Subjective means a human or rater interprets the attribute and assigns a number. In basketball, this could be the number of fouls called by the refs. In selection, this might be the score of a candidate's interview by an interviewer. Research shows that both objective and subjective measures are helpful in selection and performance evaluation. Scores are just what they mean in basketball, a number that represents the attribute or how well the candidate did on an assessment. Central tendency and variability are the averages, mean, median, and mode, and standard deviation of the scores. Central tendency tells you the average scores. The spread of the scores and standard deviation indicates how much variability there is in the scores. Percentiles are simply an indication of where an individual stands relative to all other test takers. A standard score, or a z-score, is a way to calculate an individual's score with the variability between test takers removed. Here are examples of the scores and their measurement using a data set. As you can see, central tendency is just figuring the averages, mean, median, and mode. Variability refers to the range of numbers from low to high. Standard deviation is simply a measure of how spread out the numbers are in the dataset. The standard score, or z-score, is a way to more easily compare the performance of different applicants on a test. The formula is pretty simple and can be calculated in Excel using the standardized function. In the calculations for applicants S and C, you can see that S has a score of 1.7 higher than the average, and C is 0.82 below average. Correlation simply means relationship or connection. The correlation coefficient, also known as R, shows how strong that relationship is. The closer the result is to either negative 1.0 or positive 1.0, the stronger the relationship. But remember, connection does not mean causation. For example, let's say that in August, crime goes up and ice cream sales go up. This does not mean that ice cream causes crime. In the 3 scatter plots on this page, you can see that the higher the correlation, the closer together the data points. Here's the formula for calculating the correlation coefficient of 2 columns of test scores and performance ratings. The idea is to see if test scores are related to performance. Inside the green circle shows an R of 0.58, which is a positive correlation. If the formula on the bottom of the page makes your eyes cross, there's good news. You can easily calculate R in Excel. I'll show you how in the next slide. Just put the scores for each variable in adjacent columns and enter equal correl, and voila, you have R. Here's how that complicated formula from the last slide looks in Excel. As you can see, Excel is our friend. Practically, you can interpret a high R as a strong correlation between the 2 variables. Statistically, p-value will tell you the percent of the relationship caused by chance. P-value can be calculated by running a regression in Excel. We've talked about some key concepts, including significance of measures. Now let's turn to another critical aspect, quality. Logic says that if you're going to measure something, you want to trust the measurement to be accurate. Two ways of measuring accuracy are reliability, shown here, and validity, coming to your screen soon. Reliability simply means that a measure yields the same results over and over again. For example, a tape measure is a reliable measure of physical dimensions of length, width, and height, say, of a desk. If you're conducting a personality test to measure extroversion, the test should yield the same result or very similar results over and over again. Fortunately, there are methods for measuring reliability of a test. For objective tests in the first row, you can compare results when someone or a group of someones takes the test twice. These test-taking sessions are called Time 1 and Time 2, shown as T1 and T2 in the column heading. Objective test reliability is called test-retest reliability, and it's pretty easy to understand just from its name. For objective tests, we look for the consistency of the observer or rater, hoping that you will have an inter-rater consistency between multiple raters reliability, as well as intra-rater reliability, which is consistency between the same rater at different times. But ours is not a perfect world, so naturally there's error. Measurement error is represented mathematically by realizing the actual score and has mythical true score combined with the inevitable error. Since HR and selection are dealing with humans, some amount of error is unavoidable. There are two broad categories of error: deficiency error and contamination error. Deficiency error is a whoops, forgot to measure something, and contamination error is exactly how it sounds. Whoops, I let something sneak in that was unrelated. Digging a little deeper, here are some ways contamination error can sneak into your results. Content domain means there's something unrelated to your attribute on the test. Standardization means the conditions for taking the test are not consistent. Chance response tendencies are the results of test takers guessing the answer. Rater means a rater rates people higher or lower than they should. Rating situation itself means different measures are used by raters, like asking interviewees different questions. That's why formal interviews with trained interviewers asking the same questions helps with more reliable interview results. Here's an illustration about calculating the percent of inter-rater agreement. It looks more complicated than it is. You simply count the number of times the raters agreed, the yellow boxes in the chart at the top. You can see that there are 4 times they agreed on persons A, B, D, and E. We're basically looking between rater 1 and rater 2. Then the total number of agreements, which is 5, simply counting A plus B plus C plus D plus E. Dividing the arguments by the total of all items gives you 80% agreement between rater 1 and rater 2. Here are some guidelines for minimum levels of reliabilities. In all cases here, higher is better. You have coefficient alpha, also known as Cronbach's alpha, inter-rater agreement, test-retest reliability, and intra-rater agreement. We've covered all these before. This slide deals with things to remember about measurement and reliability. Standard error of measurement simply shows the plus or minus impact of errors. This means that it's important to regard close scores between applicants as roughly equal. Relationship between reliability and validity is interesting. Let's take our desk example from earlier in the presentation. We talked about the reliability, very high, of using a tape measure to determine height, width, and depth of a desk. This high level of reliability is great, but not if what we really want to measure is weight. Therefore, reliability does not mean valid. If a measure is valid, meaning it measures what you want it to measure, reliability does have an impact. For example, you might have a valid tool for measuring let's say a scale, but if it is broken, it's unreliable and the output will limit its validity. And you'd be delighted to know that there's a formula that calculates the relationship of reliability and validity. One way to think of accuracy of measures is illustrated by this Venn diagram. The yellow circle on the left is the actual attribute, let's say a candidate's knowledge of programming languages in this example. The blue circle on the right is the measure of the knowledge of programming languages. If they overlapped 100%, that would mean that the measure is 100% accurate and contains no deficiencies or contamination. In real life, there's always some of both, so the overlap, or green area, represents the degree of accuracy of measurement. You'll notice that the terms deficiency and contamination are used for validity as they were for reliability. Measurements are used in selection primarily for their ability to predict the future. In the case of selection, the prediction of future performance. One way to test a predictor is to administer the predictor on people already performing the job, then comparing the results. In the chart here, correct predictions are found in quadrants A and C, where errors are contained in D and B. Here's an example of a test and performance comparison. We add quadrants A and C, divided by the sum of all quadrants, then multiply by 100 to get a percentage. It is of obvious importance that tests are both valid measure of the KSAOs and that they predict job success on the part of the applicant. Otherwise, predictors would not be used. Validity of predictors is determined through two types of validation studies: criterion-related or content validation. In the next several slides, we'll look at both types. As you can see from the flow chart on the right side of the screen, the process starts with identification of KSAOs through job analysis. Next is criterion measures, or a measure of performance. This can come from performance reviews. After criterion measures comes the creation of predictor measures. To check the predictor, samples are gathered from current employees or job applicants, and finally a correlation between the predictor and the criterion are calculated. This determines the validity of the measure as a predictor of performance. Here are two ways to determine validity. In the top example, a predictor or test is administered to existing employees, then compared with their actual results from their employee appraisals. In the second, which is more preferable of the two, the predictor is administered to applicants. Then, after those applicants are selected and their actual results as employees are known, they're matched with their predictor scores. This is the more time-consuming of the two methods, but thought to be more accurate in terms of adding a true applicant experience to the predictor test. Content is also sometimes called judgmental validation because it's used when there are either too few people for a sample or when no criterion measures are available. Basically, someone makes a judgment call about what problems will occur on the job and also about the correlation between a predictor and a criterion measure. Wouldn't it be nice if, once a test were proved valid for a job in one organization, it could also be valid for the same job in another organization? Well, the concept of validity generalization refers to this extension of validity. Obviously, it would be cheaper, quicker, and easier to adopt another measure that's already been validated than to have to separately validate every test or measure used in our organizations. The caution here is for organizations to consider the uniqueness of their jobs before adopting a generally valid measure. With all this talk of reliability and validity, you've probably concluded that there are legal implications of using performance predictors. There are a few important concepts to keep in mind. Three concepts are determining adverse impact, standardization of measurement, and best practices suggested by the EEOC. In our discussion of disparate impact, we learned that some employment practices have the unintended effect of causing an illegal disadvantage to a protected class. That determination is made through a compilation and analysis of statistical evidence, primarily applicant flow and applicant stock statistics. Applicant flow statistics calculate the selection rates of applicants between majority and minority or women candidates. It is expected that minorities and women are selected at least 80% as often as white men. This is called the 80% rule. Applicant stock statistics calculate the percentage of minorities and women employed by the firm versus the percentage of minorities and women in the available population. This utilization analysis is useful for both compliance and affirmative action plans. Standardization is a form of fairness. It seems fairly obvious that all applicants for the same job should be treated equally with regard to information gathering and how that information is evaluated. Employers need to ensure tests are properly validated, and if they discover adverse or disparate impact, they need to either eliminate the test or prove a BFOQ, bona fide occupational qualification, for the requirement. The EEOC lists several best practices for testing and selection that should be reviewed and followed. That's it. That's Chapter 7 and Measurement. Thanks for listening.